Right now, as you read these words, a beam of light is traveling toward you from a distance so vast that the number describing it has no meaning in any language spoken by any human being who has ever lived. That light left its source before your planet existed, before the oceans filled, before the first cell divided in the shallow warmth of some ancient sea, before the sun itself ignited. That light has been crossing the universe for longer than the Earth has been a solid object, and it is still arriving, still moving, still carrying with it the fingerprint of something so enormous, so absolute in its gravity, that the laws of physics, as we understand them, begin to tremble at its edges. That something has a name. It is called TON 618, and the first thing you need to understand about it is this: it should not exist. Not because it is fictional, not because the evidence is uncertain. It exists. The data is clear, the measurements are consistent, the mathematics confirms it across multiple independent methods of observation. TON 618 is real. But according to everything we thought we knew about how the universe builds itself, about how matter assembles and time unfolds and gravity accumulates, a black hole of this size should not have been possible in the era when this one appeared. The universe was too young, the ingredients were too sparse, the time was simply not enough. And yet here it is, a black hole containing the mass of 66 billion suns. 66 billion. Not 66 billion kilograms, not 66 billion mountains, not 66 billion planets. 66 billion entire stars, like the one that lights your world every morning, compressed into a gravitational well so deep that light itself, the fastest thing that can exist in this universe, falls inward and never returns. If you place TON 618 at the center of our solar system, its event horizon, the invisible boundary beyond which nothing escapes, would extend past the orbit of Neptune, every planet you have ever heard of, every world ever visited by a human spacecraft, every moon, every asteroid belt, every fragment of rock and ice that has ever drifted through the domain of our sun, all of it would sit comfortably inside the boundary of this single black hole. You would not need to travel to the edge of the solar system to reach the point of no return. You would already be inside it. You would already be gone. But here is what most people get wrong when they first encounter a number like this. They imagine the danger. They imagine the destruction. They think of a black hole as a hungry mouth, a consuming void, a catastrophe waiting to swallow the innocent. And while gravity of this magnitude is genuinely absolute, nothing that crosses that boundary has ever returned. Nothing ever will. The story of TON 618 is not a story of destruction. It is a story of construction. It is a story about how the universe builds its largest structures and why those structures appear in places and at times that challenge everything we thought we understood about the sequence of creation. It is a story about light so old it predates everything you have ever known. It is a story about a question that has haunted astrophysics for decades, a question that every new observation of objects like this one forces us to confront again. How does the universe make something this large, this fast, in a cosmos that had barely begun? The answer, as you will discover, is not simple. It is not clean. It does not arrive with the satisfying click of a puzzle piece finding its place. Instead, it opens into further questions, each one deeper than the last, each one revealing another layer of how little we truly understand about the first few billion years of existence. And somewhere in that uncertainty, somewhere in the honest admission that our best models struggle to account for what TON 618 simply is, there is something more valuable than a tidy explanation. There is wonder. There is the particular kind of awe that comes not from having answers, but from standing at the precise edge where human knowledge ends and the universe continues without us. If that is the kind of journey you want to take, and if you find that these quiet hours spent exploring the depths of what exists beyond everything familiar are worth something to you, do me a small favor. Hit that like button. Subscribe to this channel. It genuinely helps this reach the people who need it. The ones sitting in the dark at 2 in the morning who just want to feel the weight of something larger than their own thoughts for a little while. That small gesture means more than you might imagine. Now, get comfortable. Let the world outside wait. Let's begin. To understand what TON 618 truly is, you have to start not with the black hole itself, but with the light that tells us it exists, because you will never see TON 618 directly. No human eye has ever seen it, and no human eye ever will. It is 10.4 billion light-years away. To say that number aloud is almost meaningless. 10.4 billion light-years. Each light-year is the distance light travels in a full year, moving at roughly 186,000 miles every second. Not every hour, every second. And at that speed it takes 10.4 billion years to cross the gulf between TON 618 and the instrument we use to detect it. 10.4 billion years. The universe itself is approximately 13.8 billion years old. That means the light we receive from TON 618 left its source when the cosmos was less than 1/3 of its current age. When those photons began their journey, the Milky Way was still forming. The stars that would eventually become our sun had not yet gathered from the gas cloud that would produce them. The atoms that now make up your body were scattered across interstellar space, drifting through a universe that looked nothing like the one you inhabit. Everything that has ever happened on this planet, the formation of continents, the first organisms pulling themselves through ancient water, the rise and fall of every civilization, every war, every birth, every death, every moment of joy or suffering that has ever occurred in the entire history of life. On Earth, all of it has taken place while the light from TON 618 was still crossing the distance between there and here. Let that settle for a moment. That light is not arriving from somewhere in space. It is arriving from somewhere in time. When astronomers point their instruments at the coordinates where TON 618 sits in the sky, they are not observing a present reality. They are receiving a message from an era that ended before our world began. They are looking at a photograph of the universe as it existed 10 billion years ago. A photograph that the universe itself has been delivering one photon at a time for the entire span of Earth's existence. This is the strange, vertiginous truth at the heart of all astronomy. The night sky is not a map of what is. It is a map of what was. Every star you have ever seen with your naked eye, every smudge of galaxy visible through a backyard telescope, every faint point of light captured by the most powerful observatories on Earth, all of it is the past arriving in the present, wearing the mask of simultaneity. The further you look into space, the deeper you look into time. And TON 618, at 10.4 billion light-years, is one of the deepest glimpses we have ever managed to take. The light that carries information about it to us was already ancient before the dinosaurs walked this planet. The object itself was not discovered in a moment of dramatic revelation. It did not announce itself with a sudden flash or an unmistakable signal. Like most great discoveries in astronomy, it accumulated, slowly built from fragments of data that at first meant nothing to anyone. In the 1950s and early 1960s, radio astronomers were systematically cataloging the sky, mapping sources of radio emission, the way cartographers once mapped coastlines, methodically, patiently filling in blank spaces with coordinates and designations. Among those catalog sources was an entry recorded at the Tonantzintla Observatory in Mexico. It was labeled with the complete absence of drama that science tends to favor as TON 618, a number, a location, nothing more. It did not seem special. At the time, it was simply one radio source among thousands, a point in the sky that emitted energy at certain frequencies noted in a survey and filed away. What changed was the technology. As instruments improved, as telescopes grew more sensitive, as spectrographs became capable of finer analysis, as the ability to measure the precise wavelength of incoming light reached new levels of precision, astronomers began to look more carefully at objects like TON 618. And what they found when they finally looked carefully enough was something that the original catalogers could not have anticipated. The light from TON 618 was stretched. Not slightly, not in a way that could be explained by modest distance or ordinary motion. It was stretched, enormously shifted so far toward the red end of the spectrum that the original ultraviolet radiation it carried had been transformed into something barely recognizable. In the language of astrophysics, it had an extraordinarily high redshift. And redshift, at cosmological scales, is a measure of distance. The more the light is stretched, The further it has traveled through an expanding universe, the longer it has been in transit. When astronomers calculated what that redshift implied, they arrived at a distance of 10.4 billion light-years. They arrived at a look-back time that placed TON 618's light in an era when the universe was approximately 3 billion years old. And they arrived at a luminosity, a total energy output that was almost impossible to write down without checking the calculation multiple times. TON 618 is radiating energy at roughly 100 trillion times the luminosity of our Sun. 100 trillion. Our Sun, which is massive enough to contain more than 1 million Earths, which produces enough energy every second to power human civilization for several 100,000 years. That Sun is relative to TON 618, a candle held up to a lighthouse, a match struck in the middle of a burning city. The numbers are not poetic exaggeration. They are the result of careful measurement, cross-checked across multiple wavelengths, confirmed by independent teams using different instruments and different methods. This is a real thing. This level of power is genuinely present in the universe, and all of it is driven by a single black hole at its center, consuming matter at a rate that defies intuition, converting the gravitational energy of infalling gas into radiation so intense that it outshines entire galaxies, not by a small margin but by orders of magnitude. This is the central paradox that will follow us through everything that comes next. A black hole, by definition, is a region from which nothing escapes. Light cannot leave it. Information cannot cross back through its event horizon. It is, in the most literal physical sense, the darkest thing that can exist. And yet TON 618, powered by a black hole at its heart, is one of the brightest objects ever detected in the observable universe. The brightness does not come from the black hole itself. It comes from what happens just outside it. As matter gas dust, the remnants of stars torn apart by tidal forces, approaches the event horizon, it cannot fall straight in. The conservation of angular momentum causes it to spiral, forming a flat rotating disk of superheated plasma around the black hole's equator. This accretion disk, as it is called, is where the drama occurs. The material in that disk is compressed by gravity and shredded by friction. Temperatures in the innermost regions reach tens of millions of degrees. At those temperatures, matter does not simply glow, it radiates across the entire electromagnetic spectrum, pouring out visible light, ultraviolet radiation and X-rays in quantities that stagger the imagination. Some of that energy, a fraction carefully channeled by the black hole's immense magnetic fields, is redirected into jets. Narrow, focused beams of charged particles accelerated to nearly the speed of light fired outward from the poles of the black hole in two opposite directions, cutting through the surrounding galaxy and extending for distances that dwarf entire star systems. The black hole consumes, the accretion disk transforms, the jets distribute, and the result, visible from 10 billion light-years away, is the brilliant, unwavering point of light we call a quasar. TON 618 is a quasar, one of the most luminous ever found. And at its center, doing all of this, is 66 billion solar masses of compressed space-time, pulling at the fabric of reality with a force so absolute that the word gravity no longer feels adequate to describe it. It is something older than that, something more fundamental. It is the universe demonstrating in the most unambiguous terms possible what happens when enough mass gathers in one place and time is allowed to run its course. The question is whether time was actually enough. Because when you look at when TON 618 existed, when you consider the age of the universe at the moment that light began its journey, the mathematics becomes uncomfortable. The models strain, the standard explanations fall short. How do you build 66 billion solar masses in 3 billion years? That is the question this journey will attempt to answer. Not completely, not with the false confidence of a textbook that has already decided what it knows, but honestly, carefully, and with the full acknowledgement that the universe in this case is ahead of us. It has been ahead of us since before the Earth was born. There is a number at the center of this story. You have already heard it. 66 billion solar masses, and if you are being honest with yourself, that number did not land the way it should have. It could not have. The human mind was not built for quantities at this scale. We evolved to count prey animals on a hillside to measure the distance between one valley and the next, to track the rhythm of seasons across decades. We did not evolve to feel the weight of 66 billion suns. The number enters through the eyes, passes through the mind, and exits without leaving a mark. This is not a failure of intelligence, it is a failure of scale. And the only remedy is to build toward it slowly, one comparison at a time, until the weight of what you are trying to understand begins at least partially to press down on you. So let us begin somewhere familiar. Let us begin with a single grain of sand. Pick it up, hold it between your fingers, feel the almost imperceptible weight of it. That grain of sand represents in this analogy our sun, a single star, one ordinary yellow dwarf, sitting in an unremarkable position on one of the spiral arms of one galaxy among hundreds of billions in the observable universe. Our sun contains enough mass that if you compressed all of Earth's oceans into a droplet and then multiplied that droplet by a number too large to speak aloud, you would begin to approach its total volume. It burns through approximately 4 million metric tons of its own mass, every single second, converting that mass into energy through nuclear fusion. And it has been doing so for approximately 4.5 billion years without pause. That grain of sand, that is our sun. Now set it on a table. Next to it place another grain and another. Keep placing grains of sand one at a time until you have 4 million of them sitting in a pile on that table. 4 million grains. The pile is beginning to take up space now. It might fill a medium-sized jar. You can see it. You can hold the jar in your hands. This pile of 4 million grains of sand represents the black hole at the center of our own galaxy. Its name is Sagittarius A star. It sits approximately 26,000 light-years from Earth, hidden behind dense clouds of gas and dust at the very heart of the Milky Way. It has a mass of roughly 4 million suns. For most of human history, we did not know it existed. Its gravity influences the orbits of stars in the galactic center, stars that race around it at velocities of several thousand kilometers per second, completing full orbits in just a few years. The observations that confirmed its existence, decades of patient tracking of those stellar orbits by teams led by Reinhard Genzel and Andrea Ghez work that earned them a Nobel Prize in Physics in 2020, represent one of the great achievements of modern astronomy. 4 million solar masses, a jar full of sand, and yet Sagittarius A star, for all its mass, is relatively quiet now. It is not feeding vigorously. The gas and dust in its immediate vicinity are sparse, the accretion rate low. It is in the language astronomers sometimes use sleeping. In its active periods, which may have occurred billions of years ago when the Milky Way was younger and more turbulent, it likely blazed with far greater ferocity, but today it is subdued, a dark anchor at the center of a calm system, influencing without announcing itself. Now take that jar of 4 million grains of sand, set it on the table and look at it. Feel its weight in your mind. Let 4 million solar masses become real to you. Let the event horizon of Sagittarius A star, which spans approximately 24 million kilometers across, become something you can picture. For reference, the Sun itself is about 1.4 million kilometers in diameter. The event horizon of our galactic center's black hole is roughly 17 times wider than the star it has the mass of 4 million of. That is large. That is genuinely large. Now, multiply that jar by 16,000. 16,000 jars of sand. 16,000 times 4 million solar masses. That is 64 billion solar masses. That is approximately ton 618. Where do you put 16,000 jars of sand? They would fill a room. They would fill several rooms. They would spill out into hallways and pile against walls and overwhelm every surface available. And that image, that physical spatial image of 16,000 jars, is the closest your mind can come to grasping the mass difference between the black hole at the center of your own galaxy and the black hole at the center of ton 618 host galaxy. Sagittarius A star would fit inside ton 618's event horizon 16,000 times over. Not 16,000 stars, not 16,000 planets. The entire black hole that anchors the Milky Way, the one whose gravity holds the orbits of stars moving at thousands of kilometers per second, would fit inside Ton 618 16,000 times with room to spare. Let us try another approach, because the jar analogy, useful as it is, still does not quite carry the weight it should. The event horizon of Ton 618, the spherical boundary beyond which nothing returns, has a diameter of approximately 390 billion kilometers. Write that number out: 390,000 million kilometers. To cross that diameter, traveling at the speed of light, the fastest speed permitted by the laws of physics, would take you approximately 14.5 days. Not seconds, not minutes, days. For comparison, it takes light approximately 8 minutes to travel from the Sun to the Earth. It takes light about 4.5 hours to travel from the Sun to Neptune, the outermost planet in our solar system. Our entire solar system from the Sun to Neptune fits inside a sphere of roughly 9 billion kilometers in diameter. Ton 618's event horizon is more than 40 times wider than the orbit of Neptune. If you placed Ton 618 where our Sun currently sits, you would not need to travel to another planet to cross its event horizon. You would not need to leave Earth. You would already be inside it. Every human being who has ever lived, every structure ever built, every ocean and mountain and continent, every trace of biology and civilization and thought, all of it would already be past the point of no return. The entire Earth, along with Mars and Jupiter and Saturn and every other planet our probes have ever visited, would already be falling inward, already committed to the singularity, already beyond any conceivable rescue. And the fall would be gentle. That is perhaps the strangest thing. For stellar mass black holes, the ones that form from the collapse of individual stars and contain just a few times the mass of the Sun, the tidal forces near the event horizon are lethal long before you cross it. The difference in gravitational pull between your head and your feet becomes so extreme that it would stretch you into a thin stream of particles, a process physicists describe with characteristic understatement as spaghettification. Ton 618 does not do that, not at the horizon. Because the event horizon is so enormously wide, the gradient of gravitational force across a human body at the moment of crossing would be relatively modest. You would feel weightless. You would feel nothing unusual at all. The geometry of space-time would be curving catastrophically around you, all futures bending inexorably inward, and you would have no sensation of it whatsoever. You would cross the most absolute boundary in the physical universe and feel in that moment perfectly calm. The violence comes later deeper in as the curvature steepens toward the singularity, but at the horizon itself, with a black hole this large, the crossing is silent. That thought, the idea that you could pass through the point of no return without knowing it, that the most absolute threshold in nature could be invisible, unfelt, unmarked, is one of the more disquieting implications of general relativity. The universe does not always announce its most significant moments. Now consider what 66 billion solar masses means in terms of energy. Einstein gave us the equation that connects mass and energy: E equals mc squared. In that equation, c is the speed of light, 300 million meters per second, and because it is squared, even a small mass corresponds to an enormous amount of energy. A single gram of matter, if entirely converted, would release energy equivalent to roughly 21 kilotons of explosive force. The atomic bomb that destroyed Hiroshima released the equivalent of converting approximately 1 gram of mass into energy. The accretion disk of Ton 618 converts matter into energy not with the efficiency of a nuclear bomb that is perhaps 10% mass-to-energy conversion at most, but with an efficiency that in the innermost regions of the disk can approach 40%. 40% of the mass of everything that falls into that disk is converted directly into radiation before crossing the event horizon. The remaining 60% falls inward and adds to the black hole's mass, 40%. For comparison, the nuclear fusion that powers the Sun converts approximately 0.7% of the mass it consumes into energy. Ton 618's accretion disk is by that measure roughly 57 times more efficient than stellar nuclear fusion. It is the most efficient energy conversion process known to exist in the natural universe. The result of that efficiency applied to the quantities of matter Ton 618 was consuming during its active phase is a luminosity of 100 trillion solar luminosities. If you gathered every star in the Milky Way, 200 to 400 billion of them, and added up all of their light output, ton 618 at its peak would outshine that combined total by a factor of several hundred. This is not a metaphor. This is the measured output of a single object. It is worth pausing here to acknowledge what happens to the mind when it tries to hold all of this at once. There is a particular sensation that arises when numbers grow beyond a certain threshold. Not confusion exactly, not quite awe, though awe is part of it. It is something closer to a kind of cognitive vertigo, the feeling of reaching for a handhold and finding that the wall itself has disappeared. The numbers do not stop meaning anything, they mean exactly what they say. But the mind cannot find a foothold in them, cannot locate an experiential anchor, cannot connect them to anything in the lived world of a human being. 66 billion suns, 100 trillion times the luminosity of a star, a diameter wider than 40 orbits of Neptune, an event horizon you could cross without feeling anything inside, which every path leads to the same end inside which the concept of outside simply ceases to apply. These are not failures of imagination. They are descriptions of a reality that exists at a scale the universe built for gravity, not for consciousness. Gravity does not need to be comprehensible. It does not require that anything alive be able to picture it. It simply operates patient and absolute assembling mass over time until the result is something like ton 618. A French mathematician named Henri Poincaré once observed that mathematics is the art of giving the same name to different things. In astrophysics, that art reaches its limit at objects like this one. We give the same name black hole to something containing 3 solar masses and something containing 66 billion. We use the same word gravity to describe the force pulling an apple toward the ground and the force bending space-time around an object 40 times wider than the orbit of Neptune. The words are technically accurate, but they wear a disguise. They make the familiar and the incomprehensible sound like neighbors. They are not neighbors. They are separated by a gulf that language cannot honestly cross, and that in itself is worth knowing. It is worth sitting with the discomfort of a number that will not shrink to fit your understanding, because that discomfort is the correct response to what ton 618 actually is. It is not a failure to grasp the concept. It is the accurate recognition that the concept is larger than the mind attempting to hold it. The universe at this scale does not owe you comprehension. It only offers evidence. And the evidence assembled from light that traveled 10 billion years to reach us is unambiguous. Ton 618 exists. Its mass is real. Its gravity is absolute. Its event horizon swallows distances that dwarf everything familiar in our corner of the cosmos. The numbers do not need to feel real to be true. They only need to be measured, and they have been with extraordinary care by people who devoted years of their lives to the project of knowing what something this distant and this large actually is. What those measurements reveal is not just the size of one object. They reveal the outer boundary of what nature has so far been willing to show us. Whether anything larger exists hidden behind dust or dormant, its feeding long since ended, its light too faint or too old to detect, we do not yet know. Ton 618 is the largest because it is the largest we have found. There may be more. The universe is not in the habit of showing us everything at once. There is a photon traveling toward you right now. It has been traveling for 10.4 billion years. It left its source, the superheated edge of ton 618's accretion disk, at a moment so distant in the past that the word ancient does not begin to describe it. At the moment of its emission, the universe was approximately 3 billion years old. The cosmic web of filaments and voids that connects galaxies across hundreds of millions of light years was still assembling itself from the primordial hydrogen and helium left behind by the Big Bang. The first generation of massive stars had already lived and died, seeding space with the heavier elements their fusion had forged. But the universe was still young in the way that matters most, still chaotic, still dense with energy, still in the process of deciding what kind of place it would eventually become. That photon left during all of that. It was emitted by an atom of hydrogen, at the innermost edge of Ton 618's accretion disk, stripped of its electron by temperatures in excess of 10 million degrees, radiating energy as it spiraled toward the event horizon at a velocity approaching the speed of light. In the fraction of a second before that atom crossed the point of no return, it released a photon, a quantum of electromagnetic energy, massless, traveling instantaneously to its full velocity, moving outward through the disk, through the surrounding galaxy, and into the vast emptiness of intergalactic space. That was 10.4 billion years ago. Since then, the following things have happened. The gas cloud that would become our solar system had not yet begun to collapse. That collapse occurred approximately 4.6 billion years ago, which means that photon had already been traveling for nearly 6 billion years before the material that would eventually become the Sun, the Earth, and everything on it even began to gather. The Sun ignited roughly 4.5 billion years ago. The Earth solidified from the disk of material orbiting the young Sun approximately 4.5 billion years ago as well. The first liquid water appeared on Earth's surface, perhaps 4.4 billion years ago. The first life single-celled organisms leaving chemical traces in ancient rock appeared approximately 3.8 billion years ago. That photon was already more than 6 billion years into its journey when life began on Earth. It continued traveling while the first cells learned to photosynthesize, while oxygen began accumulating in the atmosphere, while multicellular life slowly emerged from the oceans, while the first animals crawled onto land, while forests rose and fell, while continents drifted and collided and drifted, again while the dinosaurs appeared and disappeared, while the first members of our species looked up at the same night sky we look up at now and wondered what they were seeing. All of that, all of human prehistory, all of recorded history, every civilization that has risen and collapsed, every war, every discovery, every generation of every family that has ever existed on this planet, all of it unfolded while that photon was still in transit. And then at some point in the recent past, perhaps last year, perhaps last decade, it reached a telescope. It struck a mirror or a detector array somewhere on Earth or in orbit around it. It completed a journey of 10.4 billion light years and ended its existence as a faint signal in a piece of human-made equipment. Someone read that signal, someone turned it into data. Someone used that data to tell us about Ton 618, that chain of events from a superheated atom at the edge of a black hole to a human mind understanding what that atom was doing is one of the most extraordinary sequences in the history of intelligence. And it is not metaphor or poetry. It is the literal, physical, documented process by which we know what we know about the most distant and massive objects in the universe. The technique that makes this possible is called spectroscopy, and it is, in a sense, the foundation of everything we understand about the cosmos beyond our immediate neighborhood. When light passes through a prism, or through the equivalent optical components inside a spectrograph, it separates into its constituent wavelengths. What looks like a single beam of white light reveals itself to be a spectrum of colors, a rainbow of frequencies, each carrying different amounts of energy. But that spectrum is not smooth and continuous. It is interrupted at precise and predictable locations by dark lines, gaps in the rainbow, places where specific wavelengths of light are missing. Those missing wavelengths are absorbed by atoms. Every element in the periodic table absorbs and emits light at a unique set of wavelengths, a fingerprint written in the language of quantum mechanics, determined by the specific energy levels that electrons can occupy within that element's atomic structure. Hydrogen absorbs light at certain wavelengths, helium at different ones, carbon, oxygen, silicon, iron. Each element has its own pattern, as distinctive and unambiguous as a barcode. When astronomers analyze the light from a distant object, they are reading those barcodes. They are identifying which elements are present in the gas between us and the source, and in the source itself. They are extracting chemical composition from nothing more than the color of light that has traveled billions of years. For Ton 618, those spectral lines are there. The signature of hydrogen is unmistakable. The fingerprints of other elements are present, shifted, but identifiable. But here is the key thing: they are not where they should be. They are shifted. moved from their expected positions toward the red end of the spectrum, and the amount by which they are shifted is not small. This shift is called redshift, and at cosmological scales it is caused by the expansion of the universe itself. Space is not static. It has been stretching continuously since the Big Bang, growing larger in every direction, carrying galaxies away from each other, not because they are moving through space, but because the space between them is increasing. As light travels through this expanding space, the very fabric through which it moves is being stretched, and the light stretches with it. Its wavelength increases. It shifts toward the red end of the spectrum. The further a source is from us, the more the universe has expanded during the light's travel time, and the more that light is redshifted. TON 618 has a redshift value of approximately 2.2. In the notation of cosmology, this means that the universe has expanded by a factor of more than 3 since that light was emitted. The wavelengths we detect today are more than 3 times longer than the wavelengths at which they were originally radiated. What began as ultraviolet radiation, energetic short wavelength, invisible to human eyes but detectable by the right instruments, has been stretched into visible and near-infrared light by the time it reaches us. From that single number 2.2, astronomers can calculate the distance of 10.4 billion light-years. They can determine the look-back time, the age of the universe at the moment of emission, and place TON 618 precisely within the timeline of cosmic history. The redshift is not just a curiosity. It is a coordinate in time as much as a measure of distance. But here is what the redshift reveals that goes beyond distance. When that light left TON 618, the universe was a fundamentally different place. Not just younger, structurally different. The distribution of matter, the temperature of intergalactic gas, the frequency of galaxy collisions, the abundance of available fuel for black hole growth, all of these were different in ways that matter enormously for understanding how TON 618 came to be. At a redshift of 2.2, we are looking at an era that astronomers sometimes call cosmic noon. It is the period of peak activity in the universe, the time when star formation rates were at their highest, when galaxy mergers were most frequent, when quasars like TON 618 were more common than at any other point in cosmic history. The universe at that epoch was producing stars at a rate perhaps 10 times higher than it does today. Galaxies were colliding and merging constantly, driving enormous inflows of gas toward their centers, feeding the black holes that had been growing since the universe's earliest epochs. It was a turbulent, luminous, restless era, and TON 618 was one of its brightest members. To look at its light is not merely to see a distant object. It is to witness the universe at its most active before it settled into the relative calm of its current middle age. The Milky Way today is a quiet, organized spiral, its star formation modest, its central black hole largely dormant. But 10 billion years ago, galaxies like ours were in a very different state, smaller, more chaotic, more actively building themselves from the raw material that gravity was continuously pulling inward. TON 618's light arrives as a dispatch from that era, a record of conditions that no longer exist anywhere we can directly observe in the local universe. There is a philosophical dimension to this that is easy to miss in the technical details of redshift and spectral analysis, but which becomes impossible to ignore once you sit with it long enough. When you observe TON 618, you are not observing what it is. You are observing what it was. The two things are separated by 10.4 billion years, and they may be utterly different. Consider 10.4 billion years have passed since that light was emitted. In that time, the universe has continued to evolve in every direction simultaneously. Galaxies have merged and separated. Stars have been born and have died. The intergalactic medium has been heated and cooled. The large-scale structure of the cosmos has grown more defined, the cosmic web more sharply drawn. And in the galaxy that hosts TON 618, something has been happening too. That galaxy, whatever it looked like 10 billion years ago, has not been standing still. It has continued to evolve, to interact with its neighbors, to use up its gas to age. The black hole at its center has continued to consume whatever material remained available. At some point, probably long ago, the fuel ran low. The accretion rate slowed. The brilliant quasar that we see in our data grew dim, the jets faded. The overwhelming luminosity that makes TON 618 detectable across 10 billion light-years began to quiet. The TON 618 that exists right now, in what we would call the present moment of the universe, acknowledging that simultaneity at cosmological scales is a complicated concept, is almost certainly not the blazing quasar we observe. It is probably a dormant black hole sitting at the center of an aging galaxy, its feeding long since slowed to a trickle, its glow a fraction of what it once was. It may be by now nearly invisible. We will never know for certain. The light that would tell us what TON 618 looks like today will not arrive for another 10 billion years. By the time that light reaches whatever detectors might exist to receive it, the Earth will likely be gone, consumed by the expanding sun. Whether anything remains to read that signal is a question that belongs to a future so distant it exceeds the current age of the universe. What we have and what we work with is the ancient light, the photograph from 10 billion years ago, the dispatch from cosmic noon, and from that photograph we extract everything we know. It is worth understanding how much can be extracted from so little. The light from TON 618 that reaches our instruments is extraordinarily faint. The energy carried by those photons, after 10.4 billion years of travel through an expanding universe, is a tiny fraction of what was emitted. The universe has spread that energy across an ever-increasing sphere of space, diluting it by a factor proportional to the square of the distance. By the time it reaches Earth, the flux, the energy per square meter per second, striking our detectors is almost inconceivably small. And yet, from that faint signal, astronomers can determine the object's luminosity, its total energy output, by accounting for the distance and the expansion of the universe. From the width of its spectral emission lines, they can calculate the velocity of gas orbiting the black hole, which in turn gives them the black hole's mass through the physics of orbital mechanics. From the shape of its spectrum across different wavelengths, they can infer the temperature structure of the accretion disk, the orientation of the disk relative to our line of sight, and the efficiency with which the black hole is converting infalling matter into radiation. From the polarization of the light, the way its electromagnetic waves are oriented, they can extract information about the magnetic field structure near the event horizon. From subtle variations in brightness over time, they can probe the dynamics of the innermost regions of the disk, where gas completes full orbits in a matter of hours, and where the physics of extreme gravity begins to dominate. All of this from a faint point of light that has been traveling since before the Earth existed. All of this from photons that carry the memory of their origin encoded in their wavelength, their energy, and their polarization, a memory that 10 billion years of travel through expanding space has not erased. Light, it turns out, is extraordinarily faithful to its origins. It does not forget where it came from. There is something in that faithfulness that moves beyond physics into something harder to name. The photons from TON 618 carry no intention. They have no awareness of what they are doing or where they are going. They simply move at the speed permitted by the structure of space-time through whatever space they encounter. They do not know they are being watched. They do not know that the signal they carry will one day be intercepted by a species that evolved on a small planet in an ordinary galaxy. A species that has spent the last few centuries building instruments sensitive enough to catch precisely these kinds of ancient, faint, red-shifted messengers. And yet across 10.4 billion years those photons arrived. They completed their journey. They found something waiting to receive them. The universe spent 10 billion years delivering a message, and we happened to be here when it arrived. There is something that deserves to be called extraordinary about that coincidence. We live in what cosmologists call the stelliferous era, the age of stars, when the universe is bright enough and structured enough for complex chemistry and biology to exist, but not yet so old that all fuel has been exhausted and entropy has won its long, patient war. This is an unusually informative moment in cosmic history. The ancient light from objects like TON 618 is still reaching us. The background radiation from the Big Bang is still detectable. The universe has not yet expanded so far that everything beyond our local group has receded beyond the horizon of observability. We are living in a window, a brief period measured in billions of years during which the universe is readable, during which the light from its earliest structures still arrives with enough coherence to be interpreted. Ton 618's ancient light is part of that readability. It is one of the sentences in a story that is available to us only for a cosmically limited time. Future civilizations, if any exist, billions of years from now will not have access to this light. The universe will have expanded further. The sources will have receded beyond their observable horizon, and the ancient dispatches from cosmic noon will no longer be deliverable. We are reading them now while we still can. And what they tell us, among many things, is that the universe at the age of 3 billion years was already producing objects of staggering complexity and power, that the story of cosmic structure did not begin slowly and build gently toward its current state. It began with intensity. It began with quasars blazing across the young cosmos, black holes feeding at the limits of physics, galaxies assembling themselves from the raw material of creation at rates that still challenge our models. Ton 618's light carries all of that history, 10 billion years of faithfulness to its origin delivered to us in the form of a signal so faint that it requires the most sensitive instruments humanity has ever built to detect. That signal is still arriving. Right now, as you read these words, photons from Ton 618 are reaching Earth, striking detectors, being recorded, being turned into data that someone, somewhere, is analyzing in an attempt to understand something true about the universe. The ancient light is still speaking. We are still learning to listen. Beyond the light, beyond the blazing disk and the jets, and the radiation that announces Ton 618's existence across 10 billion light-years of space, there is a place where none of that exists. No light, no heat, no motion that leads anywhere but inward. A region where the concept of outside ceases to have meaning, where the future is not a direction in time, but a direction in space, and where that direction points, without exception, without mercy, and without the possibility of appeal, toward a single inevitable destination. This is the interior of Ton 618, and the first thing you must understand about it is that it is not a place in any sense your experience has prepared you for. It is not a room, not a void, not a darkness you could illuminate if you brought a light source with you. It is a region of space-time so severely curved by mass that the ordinary relationships between space and time, the relationships that allow you to choose a direction to turn around to retrace your steps, no longer hold. Inside the event horizon of Ton 618, you cannot go back. Not because something is blocking you, not because the gravity is pulling you too strongly to overcome, but because the geometry of space-time itself has been restructured so fundamentally that the concept of back no longer has a physical referent. Every path leads inward. This is not a constraint imposed on motion from outside. It is the shape of space itself. To understand how this is possible, you need to think carefully about what an event horizon actually is. It is not a surface. It has no material substance, no thickness, no texture, no temperature. You cannot touch it or see it or feel it as you cross it. It is a mathematical boundary, a threshold in the geometry of space-time, defined by one precise condition at this location. The escape velocity equals the speed of light. Escape velocity is the speed an object needs to reach in order to break free from a gravitational field. On the surface of the Earth, escape velocity is approximately 11.2 kilometers per second. On the surface of the Sun, it is approximately 617 kilometers per second. At the event horizon of a black hole, escape velocity is exactly 300,000 kilometers per second, the speed of light, the maximum velocity permitted by the laws of physics. Nothing moves faster than light, therefore nothing escapes. The horizon is not a barrier. It is a consequence. For Ton 618, that consequence plays out across a region 390 billion kilometers in diameter. The horizon is everywhere, simultaneously, a vast, invisible, perfectly spherical threshold surrounding the black hole's mass at a distance determined by nothing more than the total amount of that mass multiplied by a simple constant. The formula is clean and elegant. The Schwarzschild radius equals 2 times the gravitational constant times the mass divided by the speed of light squared. Plug in 66 billion solar masses. The result is a boundary nearly 3 times the diameter of our entire solar system. That boundary, invisible, unfelt, absolute, is the last address the universe assigns to anything that falls inward. What happens at the moment of crossing is perhaps the most disorienting prediction in all of physics. Nothing happens. You feel nothing. There is no sensation of threshold, no flash of light, no alarm. General relativity, the theory that describes gravity as the curvature of space-time, predicts that a freely falling observer crossing the event horizon of a sufficiently large black hole would experience no local anomaly whatsoever at the moment of crossing. The physics of your immediate environment, the behavior of objects near you, the laws governing chemical reactions and biological processes would remain unchanged. You would be inside the most absolute boundary in the physical universe, and you would not know it. This is deeply unsettling for an intuition that expects dramatic events to announce themselves. We are accustomed to a world in which boundaries are marked by signs, by physical barriers, by changes in sensation. The event horizon of ton 618 marks nothing from the inside. It is only definable from outside, only meaningful in the context of what it prevents. From within, it has already done its work. It has restructured the future. It has made every direction inward, and it has done this silently without ceremony. The disquiet deepens when you consider what is happening to time. Albert Einstein's general theory of relativity, published in 1915 after years of work that Einstein himself described as the most intense intellectual struggle of his life, established a relationship between gravity and time that remains one of the most counterintuitive results in the history of science. Gravity, Einstein showed, does not merely pull objects toward mass, it slows time in the vicinity of mass. The stronger the gravitational field, the more slowly time passes relative to regions of weaker gravity. This is not a metaphor. It is not a convenient way of speaking about something that is really just a mathematical abstraction. It is a physical reality confirmed by direct measurement. The atomic clocks aboard GPS satellites orbiting Earth in a weaker gravitational field than those on the surface tick slightly faster than ground-based clocks, without corrections accounting for this difference. A difference of approximately 38 microseconds per day, GPS systems would accumulate errors of roughly 10 kilometers per day. The satellites are corrected for gravitational time dilation as a matter of engineering necessity. Einstein's strange prediction is built into the infrastructure of modern navigation. Near ton 618, the same principle applies at an incomprehensibly greater magnitude. An observer hovering at a fixed distance just outside the event horizon, ignoring for a moment the physical impossibility of hovering against gravity, this strong would experience time passing dramatically more slowly than an observer far from the black hole. The exact ratio depends on the precise distance from the horizon, and it increases without limit as that distance approaches zero. At the horizon itself, from the perspective of a distant observer, time for the hovering observer would appear to stop entirely. Their clock would appear to freeze. Their image, redshifted to invisibility, would seem to hang motionless at the threshold forever. From the falling observer's own perspective, no such freezing occurs. They experience time normally fall through the horizon in finite proper time and continue inward toward the singularity. Both perspectives are physically valid within their own reference frames. Both are predicted by the same equations. Both are in the language of relativity equally real. Two clocks measuring the same event can give fundamentally different readings, and neither is wrong. This is not an error in the theory. It is the theory. It is what space-time actually does in the vicinity of extreme mass. Deeper in past the horizon, the distortion intensifies. The concept that makes this comprehensible, or as comprehensible as it can be made, is the idea of light cones. In the geometry of space-time, every event exists within a structure called a light cone, the set of all possible future directions from that event, bounded by the paths that light itself could take. Inside a light cone, all possible futures are accessible. Outside it, nothing can reach you from that event, and you cannot reach it in return. In ordinary space-time, far from any significant mass, light cones point upward through time in every direction. You can move toward any spatial direction you choose, and the future remains open, varied, full of possibility. As you approach the event horizon of a black hole, something begins to happen to those light cones. They tilt. The future directions they define begin to point increasingly toward the center of the black hole. The range of possible futures begins to narrow. At the event horizon, the tilt is complete. The light cones have rotated until every possible future direction, including the paths that light itself would take, points inward. There is no future direction that leads away from the black hole. The geometry of space-time has been reorganized so thoroughly that escape is not merely difficult or energetically costly. It is geometrically forbidden in the same sense that moving backward in time is forbidden in ordinary space-time. Inside the horizon, space and time have traded roles. What was previously a spatial direction inward toward the center has become a temporal direction. It is the future. The singularity is not a place you can choose to visit or avoid. It is a moment you are moving toward in the same way you are moving toward next Tuesday. You cannot avoid next Tuesday. You cannot avoid the singularity. The singularity will happen. What the singularity actually is remains one of the deepest unsolved problems in theoretical physics. General relativity predicts it with mathematical precision. At the singularity, the equations describe a point of zero volume and infinite density. The curvature of spacetime becomes infinite. Every physical quantity that the theory tracks, density, temperature, curvature, diverges to values that the mathematics can no longer describe in any meaningful way. Physicists refer to this as a breakdown of the theory. Not a breakdown of reality, but a breakdown of our description of it. The equations of general relativity stop working, not because physics stops working, but because the theory was not designed to operate at these extremes. It is a classical theory, a theory of smooth, continuous space-time, and at the scale of the singularity, the universe is no longer smooth or continuous. At those densities, quantum effects become dominant. The discrete, probabilistic, fundamentally granular nature of reality, at the smallest scales, can no longer be ignored. A complete description of what happens at the singularity would require a theory of quantum gravity, a theoretical framework that successfully unites the physics of the very large, described by general relativity, with the physics of the very small, described by quantum mechanics. That framework does not yet exist. It is the most sought-after result in theoretical physics, the object of decades of work by the most capable mathematical minds of the past century. String theory, loop, quantum gravity, causal, dynamical triangulation. These are among the approaches that have been proposed, each with partial successes and significant unresolved difficulties. None of them is complete, none of them has been confirmed by experiment, and so the singularity at the center of TON 618 remains in the most honest possible terms unknown. We know it is there in the sense that the equations of general relativity point to it irresistibly. We know that something happens at the center of a black hole. We do not know in any theoretical framework that has been tested and confirmed what that something is. This is not a comfortable position for a science that prides itself on precision, but it is the honest one. There is another mystery that lives at the horizon itself, and it is perhaps more philosophically troubling than the singularity. In 1974, the physicist Stephen Hawking, working at the intersection of general relativity and quantum mechanics, derived a result that surprised nearly everyone, including himself. He showed that black holes are not perfectly black. They emit radiation, a faint thermal glow produced by quantum effects near the event horizon at a temperature inversely proportional to the black hole's mass. The mechanism involves a subtle feature of quantum mechanics. The vacuum of space is not empty. It seethes with virtual particles, pairs of particle and antiparticle that appear spontaneously from the energy of the vacuum and annihilate each other in an interval too short to violate the uncertainty principle. Near the event horizon of a black hole, something unusual can happen to these pairs. One particle may fall across the horizon while the other escapes. The escaping particle becomes real radiation, Hawking radiation, and the black hole loses a tiny amount of mass to compensate for the energy it has effectively lent to the escaping particle. For ton 618, the Hawking temperature is absurdly small, far below the temperature of the cosmic microwave background radiation that fills the universe. The radiation itself is entirely undetectable with any instrument that exists or could feasibly be built. The process by which ton 618 would lose mass through Hawking radiation and eventually evaporate would take a time so vast that writing it out in full would require scientific notation, approximately 10 to the power of 96 years. For context, the current age of the universe is approximately 10 to the power of 10 years. Ton 618 will outlast everything else we can currently observe in the universe by margins that defy description. But the theoretical existence of Hawking radiation raises a problem that Hawking himself spent decades wrestling with, and that remains unresolved: the information paradox. Quantum mechanics is built on a principle called unitarity, the idea that the evolution of a quantum system is always reversible in principle, and that information about the state of a system is never destroyed. If you know the complete quantum state of a system at any one time, you can in principle reconstruct its complete quantum state at any other time past or future. But if matter falls into a black hole, and the black hole eventually evaporates, leaving behind only thermal Hawking radiation that carries no specific information about what fell in, then the information about everything that ever crossed the horizon has been destroyed. The quantum state of all that infalling matter has been permanently erased. This violates unitarity. It is a direct contradiction between quantum mechanics and the physics of black holes. Something is wrong. Either general relativity is incomplete, or quantum mechanics is incomplete, or our understanding of what happens at the event horizon is incomplete. Physicists have proposed numerous resolutions firewalls at the horizon, holographic encoding of information on the horizon's surface, subtle correlations in the Hawking radiation that preserve information in scrambled form, but no consensus exists. The problem remains open. Ton 618 at its scale contains this paradox in its most extreme form. Everything that has fallen into it across billions of years of feeding gas clouds, stars, the remnants of smaller black Yongo pod, carries quantum information that cannot, according to quantum mechanics, be destroyed. Where that information resides, and whether it can in principle be recovered, is a question that sits at the absolute frontier of theoretical physics. It is a question the universe has posed using gravity and time as its instruments, and it has not yet received an answer. What does it mean to stand at this edge of knowledge? Not metaphorically, not rhetorically. What does it actually mean for a species that has spent its existence solving problems by looking harder, thinking more carefully, building better instruments to encounter a boundary that is not merely technical but fundamental? A boundary not imposed by the limits of current technology, but by the structure of physical law itself. The event horizon of ton 618 is not a wall that better telescopes will one day see through. It is a wall built from the geometry of space-time. No instrument can receive a signal from inside it because no signal can leave. The information about what happens at the singularity cannot reach us, not because our detectors are too small or our algorithms too simple, but because the universe has structured itself to prevent that information from traveling in the direction we require. This is the first time in the history of science that a limit on knowledge is not a temporary obstacle waiting to be overcome by cleverness, but a permanent feature of the physical world. The interior of a black hole is not merely unknown. It is unknowable in the strictest physical sense from any vantage point outside the horizon. And yet we know that something is there. We know that 66 billion solar masses of compressed space-time are doing something at the center of ton 618. We know that the laws of physics continue to operate inside, at least until the singularity is reached. We know that matter and energy falling inward do not simply cease to exist at the threshold. They continue transformed, moving through a geometry that no human mind has ever directly experienced and no instrument has ever sampled. There is a particular kind of humility that this enforces, not the false humility of pretending not to know things we do know, but the genuine humility of recognizing that the universe contains regions where the very tools of knowing, observation, measurement, the detection of signals, cannot follow. The heart of ton 618 is silent not because nothing is happening there. It is silent because silence is what the laws of physics require from that direction. And in that required silence, there is something that feels, if not comforting then, at least honest. The universe does not owe us access to all of its workings. It only offers us the portion visible from outside. What we have made of that portion, the measurements, the theories, the models, the slow accumulation of understanding, is considerable. It is by any measure one of the great achievements of conscious beings living briefly on a small planet in an ordinary corner of the cosmos. But the heart of the silence reminds us that the universe is larger than our understanding of it, that beyond every horizon we have crossed, another horizon waits, that the edge of knowledge is not a failure of science, but its permanent condition and also its permanent invitation. The silence beyond Ton 618's horizon has been there since before the Earth existed. It will be there long after the last stars have gone cold. It does not wait for us to understand it. It simply is, and we briefly and improbably are here to notice. There is a problem at the center of everything we have discussed so far. A problem that does not resolve itself the more carefully you examine it, but deepens. A problem that sits quietly behind every measurement of Ton 618's mass, every calculation of its luminosity, every model of its accretion disk present in the data, acknowledged by the researchers who produced that data, and as yet, without a fully satisfying answer. The problem is simple to state. Ton 618 should not exist. Not in the sense that the evidence for it is uncertain. The evidence is robust. Not in the sense that the physics describing it is speculative. The physics is well established. The problem is one of time, of the brutal arithmetic of cosmic history, of the gap between how long the universe had been running when Ton 618 reached its current mass, and how long our best models suggest it should take to build something this large from the ingredients available at the beginning. To understand the problem, you need to understand how black holes are supposed to grow. The standard picture begins with massive stars, stars many times heavier than the sun burning through their hydrogen fuel in millions rather than billions of years, living fast and dying violently. When such a star exhausts its fuel, the outward pressure of nuclear fusion that had been supporting its structure against gravity disappears. The core collapses in a fraction of a second. If the remaining mass is large enough, typically more than about 20 to 30 solar masses, even the catastrophic rebound of a supernova explosion cannot prevent the formation of a black hole. What remains is a collapsed object of perhaps 10 to 50 solar masses embedded in whatever remains of the stellar environment. That is the seed, 10 to 50 solar masses. From that seed, growth proceeds through accretion. The black hole pulls in surrounding gas and dust, forming an accretion disk, radiating energy and gradually increasing its mass. The rate of growth is constrained by the Eddington limit, the balance point between the gravitational pull drawing matter inward and the radiation pressure of the emitted light pushing matter outward. At the Eddington limit, a black hole of one solar mass can accrete matter at a rate that doubles its mass in approximately 45 million years, assuming it maintains that maximum rate continuously. 45 million years to double. That sounds fast on geological timescales. On cosmic timescales, it is not negligible. To grow from 10 solar masses to 66 billion solar masses through steady Eddington limited accretion, always accreting at maximum possible rate, never pausing, never slowing, the mathematics requires approximately 1.5 billion years, perhaps slightly more depending on the efficiency of the accretion process and the fraction of energy radiated away versus retained. The universe was approximately 3 billion years old when Ton 618's light was emitted when the black hole had already reached its observed mass. The first stars capable of producing black hole seeds did not appear until perhaps 100 to 200 million years after the Big Bang. That leaves at most roughly 2.8 billion years for growth. 2.8 billion years. 1.5 billion years required for perfect, continuous, uninterrupted maximum accretion from a seed of reasonable size. At first this seems to work. The numbers appear compatible if only just. A black hole seeded at 100 million years, accreting at the Eddington limit, without pause for 2.8 billion years, could in principle reach 66 billion solar masses. But the phrase "without pause" is doing enormous work in that sentence, and the moment you examine it honestly, the problem begins to unfold. Eddington limited accretion is not a default state, it is an extreme. It requires a continuous abundant supply of fuel gas that can be funneled toward the black hole at precisely the rate that keeps accretion at its maximum, without triggering so much radiation that the inflow is disrupted. In practice, accretion is episodic. It is interrupted by the very radiation it produces. When a black hole feeds vigorously, the energy it releases heats and disperses the surrounding gas, temporarily cutting off the fuel supply. The system cycles between active feeding and relative quiescence. Observed quasars in the local and intermediate universe objects we can study in greater detail because they are closer show this variability clearly. Their luminosity fluctuates on timescales of years to millennia. Their accretion rates are not constant. They are not always feeding at the Eddington limit. They are feeding as fast as their environments allow, which is often considerably slower. If TON 618's growth was similarly episodic, and there is no reason to believe it was uniquely exempt from the physics that governs every other accreting black hole we have studied, then the time available for growth shrinks significantly. Periods of quiescence do not build mass. Only the active phases contribute. And active phases in the real universe do not fill 100% of cosmic time. The arithmetic tightens, the margin narrows, and for black holes at TON 618 scale, an epoch observed at redshifts of 2 and above, the margin does not merely narrow. For some of them it disappears entirely. The time available, even under optimistic assumptions, about continuous Eddington limited accretion from the earliest possible seeds is not sufficient to explain what we observe. This is the problem. Stated plainly, our standard model of black hole formation and growth applied honestly and without special pleading cannot fully account for the existence of objects like TON 618 at the time we observe them. Something is missing from the model. Something happened in the early universe that our current understanding does not adequately capture. The question is what? The first hypothesis is the most straightforward, and it addresses the problem at its earliest stage. What if the seeds were not small? The standard picture assumes that the first black holes formed from the collapse of massive stars producing seeds of 10 to 50 solar masses. But what if under the conditions of the very early universe, before significant quantities of heavy elements had been synthesized and distributed by stellar evolution, before the interstellar medium had been enriched with carbon and oxygen and other elements that facilitate the fragmentation of gas clouds into individual stars, enormous clouds of primordial hydrogen and helium could bypass the stellar stage entirely. This is the hypothesis of direct collapse black holes. Under ordinary conditions, a collapsing gas cloud fragments, as it contracts, local overdensities within the cloud trigger the formation of individual stars before the whole cloud can collapse into a single object. The cloud breaks into pieces, each piece becoming a star. The result is a star cluster, not a single massive object. But in the early universe, there may have been conditions under which this fragmentation was suppressed. If a gas cloud was exposed to a sufficiently intense flux of ultraviolet radiation from nearby young galaxies, that radiation could dissociate molecular hydrogen, the cooling agent that allows gas to fragment efficiently and prevent the cloud from breaking into stars. Instead, the entire cloud, containing perhaps 100,000 to 10 million solar masses of gas, could collapse monolithically, directly into a single object. That object would be a black hole, not the 10 to 50 solar mass remnant of a single star, but a seed of 100,000 to 10 million solar masses formed in a single event without any intervening stellar phase. From such a seed reaching 66 billion solar masses within 2 to 3 billion years becomes dramatically more tractable. The exponential growth of accretion means that starting point matters enormously. A seed 100,000 times heavier than a stellar remnant needs roughly 40% less time to reach the same final mass under the same accretion rate. The direct collapse hypothesis is elegant. It is physically motivated. It is consistent with the known conditions of the early universe. And it has exactly one significant problem we have not yet directly observed. a direct collapse black hole in the act of formation. The observational evidence for them is indirect inferred from the properties of high redshift quasars, rather than detected as discrete events. The James Webb Space Telescope, now operating at unprecedented sensitivity in the infrared wavelengths where direct collapse signatures would appear, is actively searching. Candidates have been proposed. Confirmation remains elusive, but absence of detection is not absence of existence. The early universe is difficult to observe precisely because the light from that era is so ancient, so redshifted, so diluted by time. What we cannot yet see may nonetheless be real. The second hypothesis addresses not the size of the seed, but the rate of growth. What if TON 618's black hole was not merely accreting at the Eddington limit, but exceeding it? The Eddington limit is not a hard physical barrier in the way that the speed of light is. It is an equilibrium condition, the point at which radiation pressure balances gravity for a given mass. Under most circumstances, exceeding it means that radiation drives gas away faster than gravity can pull it in, quenching the accretion. But those circumstances assume a particular geometry, a thin, flat accretion disk radiating efficiently in all directions. Under different geometrical conditions, specifically when the accretion rate is high enough that the disk becomes thick and geometrically puffed up, when the dense inner regions trap much of the radiation before it can escape laterally, the system can sustain inflow rates substantially above the nominal Eddington limit. The trapped radiation inflates the disk, reducing the effective radiative efficiency, and the black hole can grow faster than the standard limit would suggest. This regime is called super-Eddington accretion, and it is not purely theoretical. Objects called ultraluminous X-ray sources, compact objects accreting at extreme rates, have been observed in nearby galaxies and appear to be operating in this regime. The physics is challenging, dependent on radiation magnetohydrodynamics in conditions that are difficult to simulate accurately. But the broad picture is supported by both observation and increasingly sophisticated numerical models. If TON 618's progenitor black hole underwent phases of super-Eddington accretion during periods of abundant gas supply, during major galaxy mergers for instance, when vast quantities of cold gas were funneled toward the galactic center, the growth rate could have substantially exceeded what standard Eddington limited models predict. The effective doubling time would shorten. The total time required to reach 66 billion solar masses would decrease. By how much depends on the efficiency and duration of the super-Eddington phases. Current models suggest that intermittent super-Eddington accretion combined with moderately massive seeds could plausibly produce black holes of TON 618 scale within the available time. But plausibly is not the same as certainly. The models involve enough free parameters, seed mass accretion, efficiency duty cycle, environmental conditions, that they can be tuned to fit the observations without being uniquely confirmed by them. The third hypothesis is in some ways the most radical, and it concerns not the growth of black holes, but their relationship to the structure of the universe on the largest scales. The cosmic web, the vast network of dark matter filaments, galaxy clusters, and intervening voids that defines the large-scale structure of the universe, was not assembled uniformly. Dark matter, which constitutes approximately 27% of the universe's total energy content, and which interacts with ordinary matter only through gravity, began clustering from the earliest moments after the Big Bang. The regions of highest dark matter density became the sites of the first galaxy formation, and within those densest regions, the conditions for rapid black hole growth were most favorable. If the progenitor of TON 618 formed at the intersection of multiple dark matter filaments at a cosmic node where gas was continuously supplied from several directions simultaneously, where the local density of infalling material was exceptional even by the standards of the early universe, then its growth environment was not representative of typical early universe conditions. It was the extreme tail of the distribution, a location where everything conspired to feed a growing black hole as efficiently as the physics of the era allowed. This does not solve the timing problem by changing the physics of accretion. It solves it by acknowledging that extreme objects form in extreme environments, and that the most extreme environments in the early universe were more extreme than our models calibrated on the average fully capture. The early universe was not homogeneous. It was lumpy structured, and in its densest regions capable of producing growth rates that would seem impossible if evaluated against the background average. Ton 618 may not be an anomaly that requires new physics to explain. It may be the expected product of the most favorable conditions the early universe was capable of producing, conditions that occurred rarely in only a small fraction of cosmic sites, but that occurred nonetheless. Each of these hypotheses carries partial explanatory power. Each is supported by some evidence and contradicted by none conclusively. Each points toward a different gap in our understanding of how the early universe assembled its largest structures, and they are not mutually exclusive. The most honest current assessment, the one that the researchers working on this problem tend to arrive at, after careful consideration of all the evidence, is that Ton 618 and objects like it probably required some combination of all three. A moderately massive seed perhaps produced by direct collapse, or by the rapid merging of stellar remnants in a dense early star cluster. A period or periods of super-Eddington accretion during major merger events, and an exceptionally favorable location in the cosmic web where gas supply was abundant and continuous through the critical first few billion years of growth. None of these ingredients is physically impossible. None requires a modification of the fundamental laws of physics. Together, they sketch a plausible pathway from the Big Bang to 66 billion solar masses in approximately 3 billion years. But plausible is not proven. The sketch has gaps. The early universe remains poorly observed precisely because its light is so ancient. Every new telescope that extends our reach toward higher redshifts, toward earlier epochs, reveals new surprises, new objects that strain our models, new evidence that the universe assembled itself faster and more efficiently than we had anticipated. The James Webb Space Telescope, since beginning science operations, has already found galaxies at redshifts above 10 galaxies that existed when the universe was less than 500 million years old that are more massive, more structured, and more chemically evolved than any model predicted they should be at that epoch. The early universe is consistently more organized than we expect. It builds more faster with less time than our models allocate. Ton 618 is part of that pattern. It is not an isolated anomaly. It is the most extreme representative of a broad class of objects that collectively suggest our understanding of the first few billion years of cosmic history is incomplete in ways we have not yet fully identified. There is something clarifying about that incompleteness. Science operates most powerfully, not when it is confirming what it already knows, but when it encounters something that it cannot explain. The unexplained result is the engine of discovery. It is the friction between evidence and theory that produces new understanding. When the models fit perfectly, there is nothing to learn. When they strain, when something like Ton 618 appears at a redshift and a mass that the standard picture handles only with difficulty, that strain is information. It is the universe indicating that the map needs revision. Every model we have of black hole formation was built without the benefit of seeing what the very early universe actually produced. It was built on observations of the local and intermediate universe, extrapolated backward in time through mathematics, that was never fully tested against observations at high redshift. The high redshift observations are now accumulating, and they are consistently harder to explain than expected. This is not a crisis. It is progress. It is the normal rhythm of science, the slow accumulation of anomalies, until the weight of them forces a conceptual advance. Ton 618 is one of the clearest anomalies yet identified. Its existence, measured carefully and confirmed by independent methods, places a constraint on any theory of early universe structure formation that cannot be ignored. Whatever model eventually accounts for it fully will be a better model than the ones that preceded it. That model does not yet exist, which means that Ton 618 is not merely a record holder in a catalogue of cosmic extremes. It is an open question addressed to physics, a 66 billion solar mass question mark sitting at the edge of the observable universe, 10.4 billion light-years away, patiently waiting for an answer that humanity has not yet arrived at. The universe built it before we existed to ask why. We have been asking ever since we found it. The asking is not finished. There is a temptation when thinking about something as extreme as ton 618 to treat it as an isolated phenomenon, a record holder, an outlier at the far end of a distribution, impressive in its magnitude, but disconnected from the ordinary workings of the universe, a cosmic curiosity, rather than a fundamental component of how reality organizes itself. That temptation should be resisted. Ton 618 is not an anomaly in the ecosystem of its galaxy. It is its ecosystem's defining feature. The black hole at the center of a galaxy is not a passenger, not an accidental occupant of a central location, not merely the densest thing that happened to form where the gas was thickest. It is the architect, the force around which everything else in the galaxy has assembled, evolved, and found its current form. To understand what ton 618 is, you have to understand what it does, not just to the matter that falls directly into it, but to every star, every gas cloud, every tendril of magnetic field threading through the entire galaxy that surrounds it. And to understand that, you need to start with a relationship that took decades to discover, and that remains one of the most striking empirical facts in all of astrophysics. The mass of a galaxy's central black hole is not random. It is not independent of the galaxy's other properties. It is correlated with remarkable precision with the mass of the galaxy's central bulge, the dense, roughly spherical concentration of older stars that occupies the innermost regions of most large galaxies. This relationship, discovered in the late 1990s through the work of several independent research groups, including John Megorian and his collaborators, and subsequently refined by Laura Ferraris, David Merritt, and others, into what became known as the M-sigma relation, holds across an enormous range of galaxy sizes and black hole masses, from dwarf galaxies with relatively modest central masses to the most massive elliptical galaxies in the universe. The black hole at the center is consistently approximately 0.1% of the mass of the stellar bulge surrounding it. 0.1%, always, across 5 orders of magnitude in black hole mass, across galaxies of radically different sizes, shapes, histories, and environments. The consistency of this ratio is not what you would expect if black holes and galaxies were growing independently, each following its own trajectory without awareness of the other. Independent growth would produce scatter. It would produce galaxies with massive bulges and tiny black holes, and galaxies with enormous black holes embedded in sparse stellar environments. The data shows neither. It shows a locked relationship, a coordinated growth, a coevolution so precise that it implies communication between the black hole and its galaxy across distances of tens of thousands of light years. That communication happens through energy, through radiation, through jets, through winds, through all the mechanisms by which a feeding black hole returns energy to its environment. The black hole and the galaxy do not grow in isolation. They grow in conversation, each regulating the other, each responding to what the other is doing across timescales of millions and billions of years. This process is called AGN feedback. AGN stands for active galactic nucleus, the technical term for a black hole in an active feeding phase, a category that includes quasars like ton 618. And feedback in this context means the way the energy output of that active nucleus influences the larger galaxy around it. To understand how feedback works, consider what happens when ton 618 feeds. As matter spirals into the accretion disk, the radiation produced is enormous. At ton 618's luminosity, 100 trillion solar luminosities, the pressure of that radiation on surrounding gas is immense. Gas in the immediate vicinity of the nucleus is heated, ionized, and accelerated outward. Winds of material moving at velocities of thousands of kilometers per second sweep through the host galaxy, carrying energy from the nucleus into the surrounding interstellar medium. Some of that energy heats the gas. Heated gas does not collapse easily into new stars. The temperature increase raises the thermal pressure of the gas, counteracting the gravitational compression that would otherwise trigger star formation. The result is a suppression of star formation across broad regions of the galaxy, potentially including regions thousands of light years from the nucleus itself. This is the negative feedback loop. The black hole feeds. The feeding releases energy. The energy heats surrounding gas. The heated gas resists forming stars. Fewer new stars means less stellar evolution, less supernova activity, less gas recycling, and eventually less fuel funneled toward the nucleus. The black hole's own energy output moderates the supply of material available for its continued growth. This self-regulation is precisely what the M-sigma relation implies. The black hole grows until its energy output is sufficient to heat and disperse the gas reservoir of its host galaxy's bulge. At that point, the fuel supply diminishes, growth slows, and the system reaches an equilibrium. The final black hole mass is set not by how much gas was available in total, but by the energy balance between the nucleus and the bulge, and that balance, remarkably, produces a consistent ratio across all observed systems. Ton 618 at 66 billion solar masses implies a host galaxy with a bulge mass of approximately 66 trillion solar masses, roughly 10,000 times the mass of the Milky Way's entire stellar population. The galaxy surrounding Ton 618 is accordingly one of the most massive known, its structure, its star formation history, the distribution of its stellar populations across different ages and chemical compositions, all of it bears the imprint of billions of years of interaction with the black hole at its center. Every star in that galaxy has lived its life under the gravitational and energetic influence of Ton 618. The orbits of stars in the central regions are defined by its gravity. The temperature and density of the interstellar gas throughout the galaxy has been shaped by its radiation and winds. Even the chemical composition of the galaxy, the abundance of heavy elements relative to hydrogen and helium, reflects the history of star formation that Ton 618's feedback has regulated over cosmic time. The architect does not draw blueprints. It does not plan. It operates through physics, through the blind interplay of gravity and radiation of inflow and outflow of mass and energy. But the result of that operation accumulated over billions of years is a galaxy shaped around the black hole's influence, as surely as a city is shaped around the river that supplies its water. Beyond the galaxy itself, Ton 618's influence extends further still. The jets that erupt from its poles, narrow-focused beams of plasma and charged particles accelerated to nearly the speed of light by the combined effects of the black hole's rotation and the magnetic fields threading through the innermost accretion disk, do not stop at the galaxy's edge. They penetrate the surrounding intergalactic medium, the diffuse gas that fills the space between galaxies, and extend for distances that dwarf the host galaxy itself. The physics of jet formation involves one of the most elegant processes in astrophysics. As matter spirals inward through the accretion disk, it drags magnetic field lines with it. Those field lines anchored in the disk and in the event horizon of the spinning black hole are wound into a tight helical configuration by the rotation. The energy stored in those wound magnetic fields is released by launching plasma outward along the rotation axis, the polar direction, perpendicular to the disk at relativistic velocities. The black hole's spin itself contributes energy to this process through the Blandford-Znajek mechanism, in which the rotating spacetime near the horizon extracts rotational energy from the black hole and channels it into jets. For Ton 618, the jets, if they are present and active, as seems likely given the object's luminosity and accretion rate, could extend for millions of light years. Structures larger than the distances between neighboring galaxies carrying energy and momentum from the nucleus into the surrounding cosmic environment. Where those jets terminate, they drive shock waves through the intergalactic medium, heating it, compressing it in some regions, while excavating enormous cavities in others. Those cavities, regions of extremely hot diffuse gas carved out by jet activity, have been observed around lower redshift active galaxies using X-ray telescopes. The energy deposited in them is comparable to the total energy output of trillions of stars over billions of years. In galaxy clusters where many such active galactic nuclei have operated over cosmic time, this jet-deposited energy prevents the hot intracluster gas from cooling and condensing into new stars at rates that would otherwise be catastrophically high. Without this heating, the most massive galaxy clusters would be forming stars far faster than they are observed to do. The jets regulate not just individual galaxies, but the largest gravitationally bound structures in the universe. Ton 618's jets, operating at the peak of the quasar era, contributed to this regulation on a scale proportional to its enormous energy output. The effects of its activity are encoded not just in its host galaxy, but in the large-scale structure of its surrounding cosmic environment, in the temperature of the intergalactic medium, in the distribution of gas between galaxies, in the suppression of star formation across regions of space that the jets never directly touched, but whose thermal state was altered by the energy they deposited. The architect's influence, in other words, does not stop at the property line. To bring this closer to home, to connect the grand abstraction of Ton 618's galaxy-scale influence to something more immediate, consider our own galaxy. The Milky Way has a central black hole, Sagittarius A star, with its 4 million solar masses, sits 26,000 light-years from Earth at the heart of our galaxy. Today, it is quiet. Its accretion rate is extremely low. The surrounding gas is sparse, and what gas does fall toward it does so in irregular clumps rather than in the smooth, continuous inflow that characterized Ton 618's active phase. The region around Sagittarius A star occasionally flares brief bursts of increased brightness, lasting hours to days, caused by small clumps of gas or disrupted asteroids spiraling too close. But these are whispers compared to the roar of an active quasar. It was not always so quiet. Approximately 3.5 million years ago, Sagittarius A star underwent a significantly more energetic episode. The evidence is written across the sky in the form of the Fermi bubbles, two vast lobes of gamma-ray and X-ray, emitting gas extending roughly 25,000 light-years above and below the plane of the Milky Way, detected first by the Fermi Gamma-Ray Space Telescope in 2010. These structures are the remnants of a past period of enhanced activity at the galactic center, possibly a phase of increased accretion triggered by the capture of a gas cloud or a burst of star formation near the nucleus. They are smaller and less energetic than the jets of an active quasar, but they demonstrate that even our currently dormant galactic center has its own history of outburst and feedback. Further back, much further, billions of years ago, when the Milky Way was young and still assembling itself through mergers, Sagittarius A star may have been significantly more active. The ancient stellar populations in the galactic bulge, the distribution of chemical abundances in old stars, the overall structure of the Milky Way's central regions, all of these bear the imprint of star formation and AGN activity that occurred long before the solar system formed. The quiet black hole at our galaxy's center is the dormant descendant of something that once played a role in shaping the galaxy we now inhabit in ways that left marks still visible in the distribution of its oldest stars. In that sense, Sagittarius A star and Ton 618 are not different kinds of objects. They are the same kind of object, at different moments in their life cycles, separated by mass and by the accident of what their host galaxies provided in terms of fuel. Ton 618 is what Sagittarius A star might have been, had it been given 66,000 times more mass to work with in a galaxy, 66,000 times more richly supplied with gas at the moment of formation. When astronomers observe Ton 618, when they point their instruments at its coordinates and collect the ancient light it sends us, they are in a very real sense looking at a version of our own galactic center's past. Not an identical version, not a perfect parallel, but a recognizable extreme of the same process, the same physics, the same relationship between black hole and galaxy that produced the Milky Way we live in today. The universe does not build different kinds of things at different scales. It builds the same things over and over at whatever scale the available mass and energy and time permit. There is something in this that goes beyond astrophysics, something that touches on the question of origins in a way that is literal rather than metaphorical. The atoms in your body were not made on Earth. They were forged in stars, in the nuclear furnaces of stars that lived and died before the solar system formed, scattering their contents into the interstellar medium, where they eventually condensed into the cloud that became the Sun and its planets and ultimately you. This much is well known. It is one of the genuinely beautiful results of 20th century astrophysics that we are in the most literal chemical sense made of stardust. But the story goes further. The conditions that allowed those stars to form the structure of the Milky Way's interstellar medium, the distribution of gas clouds available for stellar birth, were themselves shaped by the activity of Sagittarius A star over billions of years of feedback. The temperature and density profile of the gas that became your atoms was influenced by the history of our own galactic center's activity, and that activity at its most vigorous was a version of what TON 618 represents: a black hole in its active phase, returning energy to its galaxy, regulating the pace and location of star formation. And if we trace the chain further, if we ask what shaped the conditions that allowed Sagittarius A star to play that role, we arrive at the cosmic web, at the large-scale structure of dark matter filaments that concentrated ordinary matter into the regions where galaxies formed. At the ancient pattern of density fluctuations imprinted on the universe in its first fractions of a second, at the Big Bang itself, and whatever preceded or caused it, TON 618 at the far end of this chain is both enormously distant and strangely connected. It is not our past in a literal sense. Its host galaxy did not give rise to the Milky Way, and its black hole is not the ancestor of Sagittarius A star. But it represents the same process operating at the same epoch, driven by the same physics, building structure in the same universe. It is a cousin, not an ancestor. A parallel story, not ours, but recognizable. A window into what the universe was doing everywhere, during the era when the ingredients for everything we know were being assembled. When you look at TON 618, you are looking at the kind of process that made the kind of galaxy that eventually made the kind of star that eventually made you. The architect at the center of that ancient galaxy was building something. It did not know what it was building. It simply fed and radiated and shaped the space around it according to the laws of physics. The same laws that billions of years later, and billions of light years away, produced a species capable of looking back and recognizing the family resemblance. That recognition, quiet, precise, arrived at through decades of measurement and calculation and careful interpretation of ancient light, is itself something worth pausing on. The universe built architects, and then it built something that could see what they had made. You began this journey with a number: 66 billion solar masses, a quantity so large it refused to land properly, refused to connect to anything in lived experience, refused to be felt rather than merely noted. And now, having traveled through the physics of accretion disks and event horizons, through the arithmetic of cosmic time and the geometry of curved space-time, through the problem of a universe too young to have built what it nonetheless built, you return to that number. But you return to it differently. It is the same number. The mass has not changed. The distance has not shortened. The light is still 10.4 billion years old, still arriving faintly at instruments built by human hands on a small planet in an unremarkable corner of an ordinary galaxy. None of the facts have changed. What has changed is the context in which you hold them. 66 billion solar masses is no longer just a quantity. It is the accumulated result of a feeding process that began when the universe was a fraction of its current age, in conditions so different from the present that the word universe barely applies to both eras without qualification. It is the product of direct collapse, perhaps, or super Eddington accretion, or the exceptional density of a cosmic node where dark matter filaments converged, or some combination of all three, operating together across 3 billion years in the most favorable environment the young universe could produce. It is a gravitational well so deep that space-time itself restructures around it, that light cannot climb free of it, that time dilates at its edge in ways that make the word simultaneous meaningless. It is also a relationship between a black hole and the galaxy it shaped, between a nucleus and a bulge locked in a feedback conversation lasting billions of years, one regulating the other through energy and gravity and the slow withdrawal of fuel, between an architect and its city, neither one aware of what they were building, both following only the instructions of physics, producing together something that neither could have produced alone. And it is a message, 10.4 billion years old, still arriving. Let us be precise about what we know. because precision is the most honest form of respect for something this vast. We know that ton 618 exists, or rather that it existed, that at a moment 10.4 billion years in the past, a black hole of approximately 66 billion solar masses was consuming surrounding matter at close to the maximum rate physics permits, releasing energy at 100 trillion times the luminosity of the sun, driving jets of relativistic plasma into the surrounding intergalactic medium and shaping the host galaxy around it through the feedback of that immense energy output. We know that the light carrying this information has traveled through an expanding universe stretched from ultraviolet to visible and infrared wavelengths, diluted by the spreading of its energy across an ever-increasing sphere of space, and arrived at Earth carrying spectral fingerprints that allow us to identify the elements present, calculate the velocities of gas near the event horizon, determine the object's distance and the age of the universe at the moment of emission, and infer the mass of the black hole with reasonable confidence. We know that ton 618's event horizon spans approximately 390 billion kilometers wider than 40 orbital radii of Neptune, and that crossing it would be silent, unfelt, and absolute, that inside it every path leads inward, that the singularity at its center lies beyond the reach of our current theoretical frameworks, that the information carried by everything that has ever fallen into it is either preserved in ways we do not yet understand, or lost in ways that contradict quantum mechanics, and that either answer requires physics we have not yet written. We know that black holes like ton 618 are not isolated phenomena, but structural components of their host galaxies, architects whose energy output regulates star formation, shapes the temperature of intergalactic gas, and coordinates its own growth with the growth of the surrounding stellar system across timescales that dwarf the current age of human civilization by a factor of millions. And we know that ton 618 should not exist according to our best models, and that it does exist according to our best observations, and that the gap between those two statements is where the next generation of understanding will be inbuilt. This is what we know. It is considerably more than nothing. It is in fact extraordinary, but it is not everything. And the honest acknowledgement of what remains unknown is not a diminishment of what has been achieved. It is the precondition for achieving more. Now consider what it means that we know any of this at all. There are approximately 8 billion human beings alive on Earth at this moment. Of those 8 billion, a small fraction have spent portions of their lives studying objects like ton 618, collecting photons, analyzing spectra, writing code to extract signals from noise, building the theoretical frameworks that connect observation to understanding. They work with instruments that took decades and billions of dollars to design, build, launch, and calibrate. They collaborate across continents and languages and institutional boundaries. They publish their results for others to scrutinize, to replicate, to challenge and refine. The result of all of that effort is a number: 66 billion solar masses, a distance, a luminosity, a set of spectral lines and their redshifts, a model of an accretion disk and a jet and an event horizon, a partial answer to the question of how something this large came to exist in a universe this young. That result, that hard-won, carefully checked, honestly uncertain collection of numbers and models, is one of the things that distinguishes this species from every other form of life we have ever encountered. Not the only thing, not necessarily the most important thing, but one of them. We measure things we will never touch. We describe objects we will never visit. We construct mathematical frameworks that correctly predict the behavior of matter under conditions that no laboratory on Earth can reproduce. And then we find those conditions existing naturally in the universe and confirm that the predictions hold. We take the light from a black hole 10 billion light-years away and turn it into knowledge about the structure of space-time. No other species we know of has done this. No other species we know of has looked at the night sky and thought to ask not just what is there, but how far, how massive, how old, how formed, and used the answers to build a coherent picture of a universe that existed before this planet did. That capacity to reach outward with instruments and mathematics and careful reasoning to connect the faint signal arriving at a detector to the physics of a black hole, operating at the edge of the observable universe 10 billion years ago, is not separate from the universe. It is something the universe produced, through the same processes that built TON 618 and the Milky Way and the Sun and the Earth, and the long, slow chemistry of biological evolution. The universe eventually produced minds capable of measuring and understanding it. The universe through us is examining itself. That is not a metaphor chosen for poetic effect. It is a description of what is literally happening every time an astronomer analyzes a spectrum from a distant quasar. The atoms doing the analyzing are made of the same matter that the quasar is made of. The laws of physics governing the neurons firing in the astronomer's brain are the same laws governing the plasma spiraling into the black hole. The chain of causation connecting the Big Bang to TON 618 and the chain of causation connecting the Big Bang to the human mind reading its light are branches of the same tree. We are not observers standing outside the universe looking in. We are part of it looking at itself. And now, having traveled all of this distance through the physics and the history and the philosophy of one black hole at the edge of the observable universe, return to the simplest version of what TON 618 is. It is a place where matter fell inward and light came out. The matter fell because gravity pulled it. The light came out because energy must go somewhere, and the only direction available was outward through the accretion disk before the event horizon was reached. That light traveled for 10.4 billion years, through expanding space, losing energy to the stretching of its wavelength, diluting its intensity across an ever-growing sphere, and arrived here at this planet, at these instruments, at these minds still coherent enough to be read. That is the whole story at one level of description. Gravity pulled, light traveled, we caught it and read it. At every other level of description, the story is inexhaustible. The more carefully you look at any part of it, the physics of the accretion disk, the geometry of the event horizon, the problem of the singularity, the mystery of rapid early growth, the feedback relationship between nucleus and galaxy, ancient light's journey through the cosmic web, the more structure you find, the more questions emerge from the answers. The more the universe reveals itself to be not simpler than it appears, but more complex, more layered, more deeply organized than any previous examination suggested. This is what all the great objects of astronomy share. They are not puzzles with solutions. They are windows, and the view through them keeps extending no matter how long you look. Right now, at this moment, the light from TON 618 is still traveling. The photons that left its accretion disk 10.4 billion years ago, the ones that reached our detectors, that became the data, that became the measurements, that became the understanding, those are gone. They completed their journey. They ended as all photons end, by being absorbed, by giving their energy to whatever instrument or surface received them. But TON 618, during the billions of years of its active phase, emitted photons continuously, vast quantities of them in every direction, at every moment. The ones that happened to be aimed toward Earth arrived here. But the ones aimed in other directions toward other galaxies, other stars, other regions of space are still traveling. Right now, at this moment, photons that left TON 618 at the same time as the ones we detected are crossing regions of the universe we will never observe. Passing through galaxies we will never name, moving through the intergalactic medium in directions that do not intersect with the small blue planet, where curious minds happen to have assembled instruments to catch them. Some of those photons moving in directions away from us are still millions of light years from anything that could detect them. They will continue traveling past the boundaries of the galaxy clusters that existed in TON 618's era, through the expanding voids between the large-scale structures of the cosmic web, through regions that will grow increasingly empty as the universe continues to expand and the density of matter continues to dilute. In the very long run, across timescales measured not in billions but in trillions of years, those photons will continue their journey in an increasingly dark and empty universe. The stars will have burned out. The galaxies will have dispersed. The black holes themselves will have slowly evaporated through Hawking radiation over timescales so vast that writing them in full would require more digits than there are atoms in the observable universe. And still, some of those photons from TON 618's accretion disk will be traveling, redshifted to wavelengths so long they carry almost no energy, moving through a universe so expanded and so empty that the probability of encountering anything, any detector, any planet, any form of matter capable of absorbing them approaches zero with each passing eon. They will travel anyway. Light does not stop because there is nothing to receive it. It does not slow because no one is watching. It carries its ancient message, the quantum state of an atom near the event horizon of a 66 billion solar mass black hole, 10.4 billion years ago, without memory of its origin and without awareness of its destination, through whatever space it encounters at the only speed it knows. There is a quality to that persistence that is worth sitting with, not because it is intended, not because TON 618 sent those photons as a message, or because the universe arranged their journey with any purpose in mind. None of that is true. The photons travel because that is what photons do. The universe expands because that is what it does. Neither one knows anything about the other. Neither one cares about being witnessed. And yet, the light persists. Through 10 billion years of expanding space, through the deaths of stars and the births of galaxies, through the entire span of Earth's existence, as a solid body through the rise and extinction of everything that has lived on its surface, through the entire history of this species, from its first hesitant steps out of Africa to the construction of instruments sensitive enough to catch a few photons per second from a source 10 billion light years away, the light persisted. And we briefly and improbably were here at the right moment to catch some of it, to read it, to understand something true about what produced it. There will be a last observation of TON 618. Some future instrument pointed at its coordinates, collecting its photons with greater sensitivity than any predecessor, extracting information that current technology cannot reach. And after that observation, another and another, each one refining the picture slightly, each one adding a layer of detail to the portrait of something that existed before Earth was born. And eventually, perhaps, the questions that TON 618 currently poses will be answered. The mechanism of its formation will be understood. The physics of its interior will be described by a theory that successfully unites gravity and quantum mechanics. The relationship between its mass and the properties of its host galaxy will be explained from first principles rather than observed as an empirical correlation. That day is not today. The questions are still open. The light is still arriving. The understanding is still being built, one careful measurement at a time, by people who find that the gap between what is known and what could be known is not a source of frustration, but of wonder. That wonder, patient, precise, directed at something 66 billion times the mass of the Sun and 10 billion light-years away, is perhaps the most remarkable thing this planet has produced. Not because wonder is rare in the biological world, but because this particular wonder is coupled to the tools to pursue it, to the mathematics that describes what cannot be directly seen, to the instruments that catch light too faint for any eye, to the tradition of accumulated knowledge that allows each new observer to stand on what every previous observer learned and look a little further. The universe built TON 618 without intention and without awareness. It built us through the same physics with the capacity for both. And somewhere in that asymmetry between the blind enormity of what gravity can assemble and the small deliberate precision of what consciousness can understand, there is something that deserves to be called extraordinary. Not because it was arranged to be extraordinary, but because it is regardless of arrangement. The light from TON 618 is still traveling. It has been traveling since before this planet existed. It will continue traveling long after this planet is gone, through an expanding universe that grows darker and more diffuse with each passing eon. Those ancient photons will carry their silent record of an event that occurred 10 billion years ago, a black hole feeding at the limits of physics, a disk of superheated plasma converting gravity into light, a moment of cosmic intensity preserved in the quantum state of electromagnetic radiation, moving at 300,000 kilometers per second through whatever space it finds. Most of it will never be caught. Most of it will travel forever, undetected, unreceived, carrying its message to no one through an empty and expanding universe. But some of it reached us. A fraction of the light emitted by a single object in a universe containing hundreds of billions of galaxies found its way across 10 billion years of travel to a small planet where something had recently developed the ability to notice it. That noticing that brief, fragile, improbable act of a young species catching a few photons from an ancient black hole and turning them into understanding is the other extraordinary thing that the universe has produced. Not as impressive as TON 618 measured in solar masses, not as old measured in years, not as vast measured in light years, but aware, and in a universe that spent 10 billion years being immense and indifferent and dark awareness is not nothing. It is, in fact, the only thing we know of that can look at 66 billion solar masses of compressed space-time across 10 billion light-years of expanding universe and think, I see you. I know something about what you are. I have measured your mass and traced your light and followed your influence across the galaxy you shaped. I do not fully understand you, but I am trying, and I will keep trying. As long as the light keeps coming, and the questions keep opening, and the instruments keep reaching further into the dark, the light is still traveling. We are still here. For now, that is enough.